Actually, to the previous guest, I always ask something related to the foundations of quantum physics or the problem of, I don't know, is there a problem with fundamental quantum mechanics? And I stopped making the question because seriously, every quantum scientist say me that they don't think there's a problem, and no one seems to have philosophical problems with quantum mechanics.
Oh, for God's sake. I mean, the measurement problem's a fundamental problem. It's like absolutely baffling. Like, and it never gets any less baffling. You just learn to not think about it.
Okay, but it's seriously, like I asked the three previous guests I asked, and no one seems to have a problem. And the thing, like, apparently it seems like whatever problem stage is, you can do your work. Because I mean, I think these are really good scientists. I think they're really good quantum. I do think they understand their work and stuff. But so yes, maybe I will ask you that. Is there a problem? Is not there a problem? Why some physicists, very renowned physicists, don't have a problem? Why others yes? I don't know.
So I think it's not widely taught enough, the measurement problem.
Mm-hmm.
I only was taught it as part of my philosophy physics course. We didn't cover it in the physics course.
Okay.
It's all based around the concept of measurement and whether or not the concept of measurement is well defined enough to appear in a fundamental theorem. So textbook quantum mechanics, we're told that quantum states evolve unitarily until they're measured. And then suddenly we have this collapse of the wave function, and they evolve non-unitarily. But measurement devices are also quantum objects, and quantum objects evolve unitarily. So there's a contradiction there. And in practice, we can ignore this most of the time. Most of the time, there is a relatively clear distinction between approximately classical measurement device and our quantum system. Okay. So when we're actually doing our research, we can ignore this problem. But when you try and think about the fundamentals of what quantum mechanics actually means, we can't ignore this problem.
Okay.
And in my view, the most natural resolution is there is no collapse. Everything is unitary. And when you start to think that, you are very naturally led down the road of many worlds.
Okay.
And the most natural, consistent interpretation of quantum mechanics without modifying it is many worlds. And then that's obviously clearly baffling and crazy.
Okay.
So then you just forget about it and get on with your everyday life doing calculations because it's a bit too much.
Okay, well, I think it's a serious thing. Like a lot of physicists work in this many worlds interpretation, but I think you're the first physicist that I know that could take this very seriously in a sense that, yes, in a sense you're a proponent or you...
I don't necessarily, I'm not sure I believe in it. I don't know what I think.
But you don't see it as a crackpot. You don't see it as crackpot.
No, I think it's like, if you just intake quantum mechanics at face value, that's what you end up with. Okay. And then obviously it's crazy, but it's also what you end up with if you take quantum mechanics at face value, and quantum mechanics at face value quantum mechanics is incredibly well verified. It's been used to make novel, unexpected predictions that then be verified by experiments. It's one of the most accurate theories we have, up to caveats about consistency with gravity. So if this theory at face value implies many worlds, it's something that we should think about and see whether we could understand. And I'm not sure whether that is the right interpretation. I don't know whether the hope is maybe we will one day come along and find some modification of quantum mechanics that somehow does away with the measurement problem. But I do think it's a serious interpretation that requires thinking about, even if we eventually decide that it's wrong.
Okay. I guess one of the counter arguments would be that from what I read, it seems like some scientists find it as scientific in the sense that if there's not a way to experimentally prove this many words, it seems like for some it could not be actually called science. So I don't know if this is a problem for you or do you find it problematic. I guess it is problematic at the very least, or not for me.
It's tricky because I still maintain that it is. So if we have evidence for superpositions at the microscopic scale.
Okay.
And we have no evidence for dynamical collapse, that these superpositions are actually broken down as you go to a macroscopic scale. Given we don't have evidence for that, it would seem that you effectively have many worlds. I need to think about it further. I don't really see it as a scientific. The more fundamental problems is understanding probability.
Okay. I guess something related to normalization, maybe? Or...
Like how you get out the ball, how you understand probability in a universe where you end up with a superposition of everything.
Okay.
I find that a more fundamental problem. But I don't fully understand the claim that it's ascientific, because it's more... Okay, I find it more ascientific to try and do something like, say, measurement special.
What is measurements?
That say that you have a collapse.
Okay.
That somehow measurements are different. Unless you have evidence for it. If you can find evidence of an abacus collapse, fine. But there are some of these weird sort of quantum relativism approaches that I really, really, really don't understand. I cannot get my head around them. They say they're Copenhagen done well, but I find them absolutely baffling because they seem to rely on some fundamental distinction between a quantum system and a quantum system and a quantum measurement. And that to me seems ascientific, because that fundamentally isn't that distinction.
Yeah, maybe for people who are not that familiar, at least with me, I think with most students, is that when you enter like a university level quantum mechanics course, one of the first things that you encounter is these postulates, right? Like they say, okay, so if you measure, you make a measurement. It's not exactly defined what is a measurement, but if you make a measurement and your wave function collapse, and it's something that happens, but it's not, I mean, it's not something that it was like sort of like analytically derived, or that there's like really a convincing explanation of why it's that way. We just know that it happens, or like at least that's one of the, according to this interpretation of Copenhagen, it seems like this is something that happens when we observe.
When did it happen? When does something cease to evolve unitarily and suddenly obey this collapse postulate? That's not verified.
Yeah, I also was reading because I mean there is some people relate the phrase by Einstein, I think, about like spooky effects by entanglement. But I was reading another view that apparently some scientist was reading that it was malinterpreted, in the sense that Einstein referred more to the fact that if you have like a sort of like a wave function in superposition, how did it happen to be, I don't know, to have like this wave function is sparse, or if it had many options, how did it pass from the fact that being in superposition to actually acquire one definitive value? So apparently he had also a lot of problems with this view of quantum mechanics, but I don't know. Yes. Okay, so well, at least we can say that there is a philosophical problem with quantum mechanics. The measurement problem, there is a view, but which is strange, because I mean the truth is also you can do quantum research on quantum physics without not necessarily getting involved with this problem.
The point is, in practice, we have decoherence. And in practice, moderately large measurements end up basically decohering at the position basis. And so in practice, we have a relatively clear notion of the distinction between a quantum system and a measurement device. And that means in practice, we can ignore these issues. But that doesn't stop there being a fundamental issue that actually the notion of a measurement is ill-defined.
Okay. I'm gonna have to think about this. Okay, yes. But yeah, I find this subject very interesting. It's also, in a way, difficult, because I think it's very hard. I don't want to say impossible, but it's very difficult to come up with experiments, or I think so far no one has come up with an experiment. I don't know if it's possible to come up with an experiment to sort of like distinguish between different interpretations. So I guess this will be one of the major problems. So I don't know, experimental evidence, what you...
So dynamical collapse is nice and scientific.
Okay.
The idea that actually there is some non-linearity that kicks in a certain length scale, and people have done experiments looking for that, and the point is they don't find anything.
Okay.
So that one at least is testable. The rest, trying to distinguish between many worlds, Bowlby mechanics, and something like quantum relativism. I don't know whether that can be explained.
Yeah. But I mean, yes, I mean, one could never know. For example, I mean, one of the greatest results in quantum mechanics, I think, or one of the greatest advances, at least in fundamental quantum mechanics, was because of the Bell inequalities. So, I mean, it's not easy. I don't know if it's possible, but there are certain ways of tackle some fundamental problems in quantum mechanics, I believe. So, I mean, we don't really know, but like you cannot, I guess it will be not convenient to give up and say, oh, no, we can, but rather like keep searching and try to find out.
Yeah, though I think the game there is often about just at the level of foundations, it's can you formulate a consistent theory. So my impression, it seems to me that quantum relativism just isn't consistent.
Okay.
Many worlds, despite being crazy, is at least consistent up to maybe some caveats about how you understand probability. Okay. And then Bowlby mechanics, I think that is also consistent, but the argument against that one is it posits the existence of these sort of postulate. It has these like what do they even call them? It's got these like little particles. And I think, as far as I understand, that is a consistent theory, but then you could just kind of apply Occam's razor to it and say, what's the point in adding these empirically inaccessible particles? Now, of course, you could say the same to many worlds. What's the point in positing these extra worlds? Mm-hmm. But at least these extra worlds don't require adding anything to the theory. Mm-hmm. But Bowlby mechanics, you have to posit the existence of these point-like particles and these trajectories. So you actually are adding something to the theory. Mm-hmm. So by Occam's razor, you almost apply double many worlds, unless you're someone that then tries to apply Occam's razor to many worlds, objecting to it's those kind of arguments rather than expressly that seems.
Okay, I see.
It's arguments about consistency, whether the theories are consistent and whether they, which one works best with Occam's razor.
Okay, well, okay, so I have to think about this. But yeah, honestly, it's very refreshing to have a different opinion to someone that's saying that you don't care or stuff, because sometimes I get this kind of answers, sometimes people don't care, which I don't judge. I don't know. I want to just clarify that I think these are very good scientists. I think these are very good scientists, but...
Get someone who works with positive physics. They would all be turning in their graves with my attempts to describe the different theories right now, sort of dredging out old memories from studying them. But yeah, if you want to talk to someone about quantum foundations, get someone working with quantum foundations, it'll definitely get people to engage there.